So this talk's going to be a little bit different in the following sense. I'm really going to focus on what we need to do to get these technologies used. And you can interrupt anytime you want. Part of this talk, some of you will have heard before. But given the excellent talks by Brian and David, right? You know, I owe some tutorial. So let me just first start, and I don't need to spend much time on this because the previous speakers did a great job. I just want to contrast confidential computing with the other technologies. And I hope I'm relatively fair. Both MPC and homomorphic encryption require specialized programming. There are tools and libraries to help you do it faster, but specialized program, so they typically are applied only to a fairly small number of problems. They do have a different security model that is based on crypto, which is always a nice model to have. They don't protect the data when it's unencrypted, when you start it out on machines which might have malware and stuff like that. They don't do that. They don't pretend to do stuff like that. Differential privacy, and they're somewhat expensive. In fact, maybe very expensive. I don't want to, you know, if you move to the Amazon cloud because you wanted to save 40% on your computing bill, you probably wouldn't use homomorphic encryption, you know, on a cloud to save money. Differential privacy, as a previous speaker said, works on aggregate data. It doesn't protect the data while the lookup is happening, while you're getting the information. So if there's malware on that machine, if there was an insider attack, any of that stuff, the information's out. Trusted third party is great if you have a really diligent, smart, uncorruptible third party, but then you have to do that, and maybe those guys are expensive. Confidential computing, the security model is the hardware is the thing you rely on. And in a slightly lower voice, it's and that you wrote the program correctly. In fact, that's typically the hard thing. So those are the characteristics of a confidential computing thing. And in principle, to break the security model, you have to break the hardware, or you have to screw up when you wrote the program you're using in confidential computing. The other nice thing is the programming model in a confidential computing environment is almost exactly the same as anywhere else. So, you know, you don't have to train people for a week, a couple of months. I did an experiment at Google where I had a group. I said, here's the instructions about, it wasn't confidential computing, it was something else, a similar thing. You have 2 hours to read it, then I want you to write a program. And most of the people did the right thing. You know, so it's general purpose. It works anywhere. Lately, the big selling point is, well, it'll protect you from the cloud providers knowing your data. And I guess that's something. But to be honest, people need to use it everywhere. Even if you use confidential computing, that does not mean you don't want to mix it with other technology. So Brian talked about threshold computing. You might well have the computation in several confidential computing containers and use a threshold scheme to make sure that if several of them are broken, you don't lose. And the idea is, well, you know, it takes hundreds or thousands of dollars to break a single piece of hardware, and maybe the hardware is places where you think they're, you know, generally honest. So you might combine the things. It also protects against insider attacks. Insiders never see anything, period, if you write your program right. Okay, so that's the deal. Let me just say how it works. And saying how it works is actually a lot easier than explaining the properties. So there are exactly 4 things a confidential computing platform, hardware, think of it. And typically the best instantiation is hardware, and one place does all these things, like the CPU package, that you're not relying on I/O devices or anything else for the things I'm about to tell you. And the first thing has to do is the program, whatever you give it as a program, has to be isolated. Nothing else on the machine, no intervention by a super user on the machine lets it have access to the program's address space or its data, period. The data is encrypted, and typically the mechanism is it's encrypted and it's only decrypted in SRAM, and in the cache, period. The second thing is you need to know that the program is the one you expected. It's measurement, and you can think of that as a hash of the program or something, some universal, unforgeable way to identify the program and all its elements, and including its data. So if there are public keys in the program that are used as a root of trust for something, if you change them, you don't get the same measurement. The third thing is secret storage. This program will take data that's encrypted, that only it can decrypt. And in order to make that statement, it has to have keys that only it sees. And the mechanism, roughly, is it will hand a secret to this platform and say, I want you to save this secret for me. And the platform will encrypt it with an internal key, include the measurement, along with the measurement of the program, encrypt it and give it back. And the next time you want that secret, you give it back to the platform, it decrypts it, looks at the measurement, says, oh yeah, this guy is the right guy, and gives back the secret. So that's the third thing. And the final thing, the trust establishment, and Paul was probably the guy who came up with this name, is attestation. So the platform can sign a statement that says, the program with this measurement on this platform with these characteristics asked me to tell you this, sign the platform. And typically the thing it asks you to say is a public key. And the meaning of that public key is, I've made up this public key, only I have the private key. So if I prove possession of that private key, it's me and nobody else, and I only can use it in this trusted environment. So those are characteristics. Yeah, I'm sorry. I should have animated along the way. So it's actually principled security in the sense that you can say why you trust the thing. It's not exactly a statistical thing. It's not very complicated. It's program's isolated, the program's correct. Here's how it's written. It can't do anything I don't expect. And to guard the confidentiality and integrity of the program, it has its own secrets. And if it wants to share, it wants to work with other programs, it uses this attestation mechanism. Okay. And there are lots of applications. Probably the most popular one is data sharing right now. But, so far, its biggest commercial use is key stores and HSMs, because they're nice, relatively simple programs. So the companies who make money on confidential computing now mostly implement key stores and HSMs for people. Shared data access, which I'll talk about, to critical to sensitive data like personally identifying information, anything like that. The promise is only the program sees this information, no person. So it could be used for that. Safe program execution, zero trust. If you believe in zero trust, you really need to know what the program is. I don't know how you do it, actually. Collaborative machine learning, motion planning. We had somebody write something for our system where inside a factory, a robot would share data with a server. It would do the motion planning for it, and the robot would get move down aisle 7 or whatever it was. And the owner of the server could guarantee that he or she or they didn't see the data. Secure document sharing, factory automation, I think will be an important one. If you have a factory or any infrastructure and you want to be 100% or nearly 100%, you want to be very sure that it doesn't do anything it's not supposed to, and it does do the things it's supposed to, even in the presence of bad insiders. This mechanism principle could do it. It also, if you have it at the edge, guarantees provenance of data from sensors all the way to collection in a server. So it helps with that. I'm not going to do that one. So that's it. Okay, so that's the deal, and I think it's a fine technology. And the question then arises: well, what do you have to do to use it, and why don't people use it more? And that's actually, I'm going to kind of focus on that. So there are barriers to using it. Probably the most important barrier is you have to know to use these primitives and how to use them. And the primitives are different on every platform. So you use AMD SEV, there's one way to do it. If you use TrustZone, there's another way to do it. If you use SEV, there's yet another way to, not SEV, what's the Intel one called? SGX, right. There's still another way to do it. And in fact, the thing I'm about to tell you about, the way it started is we started doing interfaces of these, and I said, it should not take me 4 months to write a program to these things. So I wanted to overcome all these barriers. And let me be very concrete about what I mean. One of the things I really loved when I was at Bell Labs was Linux. I learned Linux early. I can go to any Linux machine based on my learning back in 1980 something and use it quickly. I know how it works. I know what it does. It has a nice, simple to understand model. And if I want to write a program, just like in the tutorials, I can copy and paste. And I can get a program working really quickly. Now, of course, when you copy and paste, you have to be careful about writing the program. But the basic idea is you can get started really quickly with Linux. The other problems are, I guess, barriers are, these programs come with policy. Like one program has to trust a bunch of other programs. It needs to know how to do that. And you don't want to manage that. You want to make sure it's scalable so that however you do this policy and agreement, the guy at Google, where I was when I did one of the versions of this, doesn't say we can't possibly use it because it will only work on 10 machines at once. That you can't do that. In fact, Rob probably shouldn't interfere with their deployment model at all. Program policy is kind of at the basis of this. It needs to be simple enough for these programmers, I told you, didn't have to learn too much to understand, and simple to express and auditable. You have to know what's going on. So those are the barriers. The other barrier is there's not enough of the hardware available. So one of the things Paul and I are working on is trying to, port the thing I'll tell you about to lots of other platforms. They may not be perfect from the hardware point of view, but you really need enough hardware to make this work. It's generally available mostly on servers. And I personally would like to see much more availability on clients. Okay, that's the deal. This is the list of things you'd have to do as a programmer if you took one of these platforms and wanted to write it yourself. So having worked at Microsoft, where any objection that took like more than 2 seconds for somebody to overcome was the reason they couldn't do something, I said, you know what, we really need a framework, think of it as an API, where people can just sit down, take a well-written program and turn it into a confidential computing program. My goal was literally within an hour. And when you did that, I wanted to make sure that program ran on any confidential computing platform, not just the one you got stuck with when your IT department bought the hardware. The thing I'm most going to talk about in the beginning is a thing called a certifier framework, which does this. There's a simple API. In fact, it's so simple, I'm going to show it to you. So you could literally write a program after this. We supported lots of different platforms. Probably the most prominent is AMD SEV, but we did Samsung had an ARM implementation of something like this. RISC-V had something. Intel had a bunch of stuff. We're thinking about porting it to an Android platform right now. I would love to see some edge programs, especially if you're going to use factory automation, which had stuff like this on ARM architectures. Okay, the API is minimalist. It doesn't depend on your policy. The program policy is enforced automatically, as I'll show you in a second. So you don't have to write complicated rules to write the program. In principle, it enables new services. Again, we can get rid of Brian's trusted third party. Our original example was you have a bank, 3 banks, they want to share their threat data. Here's how we got whacked. They don't trust each other. They don't trust the third party. They could write a program together, look at it, make sure the program's well written, run it in a confidential computing container with policy they've all seen and signed. And that program could do the analysis, send out the answer, and they could be pretty confident that nobody has seen the wrinkles in their organization. Okay, so it consists of two parts. The first is the API I just talked to you about. So you're Joe programmer, you want to take your program that does whatever and turn it into a confidential computing program, use that API. The policy is managed typically at a server, and there are several reasons to do this. If I had to keep the policy on the client all the time, every time I upgraded the client or wanted to trust another client, I would have to change the program. That's kind of a disaster. The model of using a server is the server maintains the policy, and in the end, when you do the attestation that says, here's my public key, your measurement appears, and you will only get that certificate if the program with that measurement complies with the security policy in that security domain. So somebody will have looked at the program, says this does the right stuff, and sign that certificate. When somebody adds a program to that, guy at the server does that. You, as a relying party on your client, your machine, which we'll call a client for a minute, doesn't need to know anything new. You just get another certificate with another measurement that says you can trust this guy. Okay. You can run it, the service, anywhere. I mean, it doesn't really, I said server, but that was like a fancy name. You could run it under your desk if you want, but it's important that the certifier service be the root of the security domain. You can run it in the cloud. If you're a cloud provider, probably you say, let us run it for you. You don't have to. I once gave a talk to, I guess it was an intelligence agency, and I said, well, look, you can run it yourself. You can run it in the cloud. You can trust the third party. And some guy interrupted me and say, what is this, an IQ test? I run it myself, right? And you know that's obviously the safest thing to do. And it doesn't require a lot of work, so it's okay. All right. There are only 3 concepts you need to know to use this framework. A security domain is a domain in which the same kind of policy is enforced. For example, the 3 banks are in a security domain, and the promise is you don't give any of my data, and you only do this kind of analysis on the stuff, and you never, ever, ever, ever send out, have my data unprotected, encrypted outside this container, period. In a model where you're sharing data among 8 people, you know, you're doing machine learning, and there's a program that says, I won't disclose any data unless it comes with a certificate from the owner of that data that says I can share it with that guy. The second thing is an authenticated channel. If I want to cooperate with another confidential computing, could be the same program, just a copy of it, or it could be another program. I have to establish trust. That means the 2 programs ought to be able to share data and never disclose it to an outside guy. And the mechanism is very simple. It's basically client auth HTTPS, and the key you use is that public key you got when you got certified. So 2 of these guys can open up a channel, they can share data, they can do whatever they want, and nobody gets to see it but them. Now, you've expanded the TCB in the sense that both programs had better be written correctly, but that's it. And we also have a policy store. So, you know, doing this right means, you know, regenerating keys, making up keys, storing some information, blah, 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 blah. And I wanted to eliminate the need 98% of the time for people to know anything about that. So there's a policy store that stores policy, and most of the time you don't have to touch it. If you want to do something special, you can, but you don't have to. This is literally the API. And I'll read it to you at this, you know, I will be at a disadvantage compared to earlier speakers who are much clearer. So the first line is just, here's the public key algorithm I want to use. In this case, it's RSA 2048. Here is the symmetric algorithm I want to use, like when I talk over an encrypted channel, or I save a encrypted file, whatever, that kind of stuff. That's that. That's all you do about the crypto. The second line says, okay, start me up an instance of this protection mechanism, and I'm going to use it on an AMD SEV enclave. That's the only place, that line is the only thing that depends on the underlying platform. I'm going to use it. I'm not going to explain this next thing. I want the enclave to do authentication for me. It turns out you can also appoint people to do attestation for you, but that's, this is the name of this policy, encrypted policy store where you can stuff that you want to remember. So that's it for the declarations. The next statement says, initialize me. Initialize the enclave. Different enclaves have different initialization mechanisms that we don't want anybody to know, or have to know anyway. Here's my policy key. This is the root of trust for the policy in this security domain. Here it is. That policy key is actually in the program. So that program, part of its contract with the rest of the world is I won't do anything that hasn't been approved by that policy key. The private key corresponding to that public policy key. Init, cold init just means, okay, make up the keys too, because you haven't made them before. There's a warm init if that's ready. And the fourth thing, and this is the only thing you do for policy, is certify me. Certify me packages up all the evidence the certifier service needs to know to say, yeah, this is one of the trusted programs in the security domain. And that's it. After that, you're done. You have all your keys. You have to know a little bit about crypto, like, there's an API to encrypt this file for me, that kind of stuff. But that's it. Those are all the new concepts. And then you just stick your application in there. And the last line is how you start an authentic secure channel. So it's just one call. We did a bunch, again, in the spirit of Linux, we wanted people to copy and paste. So there are a bunch of examples with all the platforms that we put in our repository. It's an open source repository. And in this simple case, there's a program which, when acting as a server, or which acting as client, sends a message over an authenticated channel to a server, says, hi, I'm your secret client. And then the server sends back a message, hi, from your secret server. That's really all it does. But that's all you need to know to write these programs. Yeah. So we have a simulated enclave, so you can write these programs anywhere. You don't have to have the hardware to do it. AMD SEV, SGX, ARM CCA, which is the name of the thing I couldn't remember, RISC-V. We haven't done TDX yet. In principle, it's almost the same as SEV SMP, but it's based on SGX and has some, it hasn't been popular yet, so I just haven't quite gotten around to doing it. And once you have a secure enclave, let's say you're in an OS, you can actually have sub-enclaves which use, say, the operating system to guarantee isolation measurement, blah, 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 blah. So you can actually have a service which acts as a hardware-like platform for individual applications. So in principle, you can have a virtual machine, and the virtual machine can spawn applications which are, you can think of as an enclave. And if you trust the isolation mechanisms of the OS, those are just as good as the other ones. So that's the deal. Yeah. So it's supposed to be simple. You probably got that by now. The service, again, is very simple. The service is written in Go. And what it does is compare policy to this evidence offered up by Certify Me. And this is literally the policy for a program. Uses Butler-Lampson's spooky sudsy thing. The first statement, it's actually an axiom, is the policy key in the program is the root of trust. You can trust it. If it says something's okay, it's okay. The second statement is the policy key says this measurement can be trusted. That's how you tell the certifier service that means this program is trusted. The program with this hash, this unforgeable identity, is in the security domain. It will obey the rules. The third statement tip is, well, the policy key says a particular platform key, let's say Intel's key, can be trusted for appointing a sub-attestation thing. And the last rule is a platform key says this particular attestation key on this particular machine can be trusted for attestation. That's it. And as we'll talk later about how to get it, these are the only rules that are mandatory for somebody to have. Now, if you have granular protection, for programs, there are more rules. Oh, or if you have a echo. But those are kept separate. I'll talk to you about it later. This is the only thing you need to understand for most programs. And then just as a benefit, when the certifier certifies something, it actually emits a proof of why this program should be trusted. And it will use those rules I told you a minute ago. The purpose of that proof is to say the program key, the key the program offered up to authenticate it, can be trusted for authentication. That's the goal of the proof. And now any program in this security domain should be able to do that. Okay, so if you have been at other talks, some, almost all of this will seem familiar. Now it's the new stuff. So we're trying, I think one of the things we're trying to do is get it on more platforms. It's hard to get people to use new technology unless it's pretty readily available. So we're kind of, I wouldn't say indiscriminate, but we will generally port it to platforms, even if they're not perfect. Like Android doesn't have the same kind of protections as, say, SEV. But that's okay, it has some, and you can understand what they are. There's a new technology coming from ARM that I expect to port to quickly. RISC-V, in addition to Keystone, which is an early version of this, has some new stuff coming out. We hope other platforms come around and they will hopefully use standard roots of trust like DICE and Python and all that stuff. We really want more applications. So we did examples with machine learning, with secure communication, but we want general data sharing. So in addition to all this, I implemented a sort of an ACL system that basically says the guy who owns this public key can access these files, the guy who owns this public key owns this file. So again, it's a Unix-like interface to do sharing information without a lot of overhead, without a lot of programming, I guess I'd say. Something like this seems to be very important in physical infrastructure, cyber physical infrastructure. If you have let's just pick an example, car, which can, do damage. If the program software is telling it to do something wrong, you want this. If you want the car to share its sensor information with other cars so that they can make safer decisions, you want to make absolutely sure that that information hasn't been tampered with. I don't really know another good way to do this. Critical infrastructure, a lot of our critical infrastructure, nobody's there. We don't want insiders to, to break in or do stuff. So if you want secure critical infrastructure, this is a mechanism to do that. Critical interactions, I mentioned the car. I guess the car is a good example of critical interactions. Another is factory automation. If you're Intel and there's something which messes with the wafer in some way, you don't want it to do the wrong thing. That's bad. Interestingly, at a place as complicated as Intel, the guys who supplied the machine that does that and the software that manages that are not you. So at times you might have to talk to that and get advice about how to do something, and you don't want them to know what you're up to. So this mechanism protects that just like robot, blah, blah, blah. We added more capability for fine-grained access control. The hard problem is, and one we'd like to solve, in not just the simple case, it's easier if it's a simple program, is how do you compose components that are protected with this mechanism? How do you compose them safely? And sometimes, because there's not going to be a lot of confidential computing programs at first, maybe you want to have a confidential computing program that does some root protection, I don't know, keys, or it decrypts the data, but then interacts with an unprotected program. How do you compose these and get sensible guarantees about what the security is going to be? And an example of that, actually, I think Amazon has done this. They have a confidential computing-like thing that basically sits on the network card and will only talk to, Amazon stuff inside the data center. That it's a guard. It won't boot anything unless it comes over that, none of that stuff. So that's a simple application. And I guess that's it. Okay, so now it gets a little more artsy craftsy. So what am I trying to do? What I'm advising people to do? People care about outcomes, not philosophy. So for example, I mentioned clients. It's very hard right now to protect user I/O, the keyboard, the mouse. You want to make sure that the screen, when it says this is coming from your protected program, really is, that's from your protected program. And on clients, that's a little bit hit or miss right now. There are kind of ways around that. But I would say in Butler Lampson's perfect is the enemy of the good, is your program, even on a client, is still much safer if you use this. Much, much, much safer. So you should use it, even if it's not perfect because of the underlying platform. When you can make specific, principled, verifiable claims about the security, information flow, all that stuff Fred talked about a few meetings ago, it's a good idea to do. If it's a simple thing and people understand it and you can package it up, you should certainly do that. I'm not arguing that it should be the Wild West. So you should certainly do that. Perfect is the enemy of good. Okay, we've done that. We really would like to see progress. So I mentioned maybe a confidential computing program provides a guard to stuff that's kind of not very secure. And if you bring a security guy says, well, maybe I can break this 6 other ways. And maybe it's true, maybe it's not, but it's harder. And if people start somewhere, they can start changing the components to make them safer and do the right thing. So it's, as a practical matter, it's like hyper important to get people to use it. That's been a major barrier. I remember being at one big company where I wanted them to use it. And they go through a list of objections like this. And when I overcame them, a guy looked at me, and you might have been at this meeting, and they said, but if you do that, they'll use it. And he would say, yeah, that's the idea. But they didn't think that was such a great idea. Don't complicate deployment. Everything I told you with the APIs and certifier service doesn't change the way Amazon, Fred, me, anybody installs program, distributes them, nothing. It doesn't have any effect on it. The only thing we rely on is being able to make a communication channel connection, like we'll call it the internet for a minute. That's the only thing it relies on. We don't want to create fragile legacy. I mentioned we did a granular file level protection thing, but I don't want everybody to have to use that. So if you just need the basic stuff, you can just use the basic stuff. And if somebody comes along and says, oh my God, I have a million times harder problem, your simple ACL system, despite the fact it's been used for 80 years by other people, won't do what I want, we'll say, fine, go ahead, do your own. You can use the confidential computing thing. You want to allow useful complements. So policy, you want better languages to implement programs. You want a good policy language if it's going to be a distributed, like data sharing thing. We want people to be able to do that. Maybe the person from DLR will talk about that a little bit. Security is not a luxury, but along the lines of, it doesn't have to be perfect. Unix is a tremendous success. Nobody I know, maybe, I still have the code. Nobody I know uses the 1978 version of Unix that Thompson and Ritchie wrote. It was a nice program. It was only 10,000 lines of code. It was great. As I said, it was a model for everything that came afterwards. But it's not a failure that people have done more stuff and made it better. But you got to get in the game.